as we ended class on Friday, I think it was Caitlin, asked me, or one of the two Caitlins, asked me if we're going to have a review lecture. And I said, I don't know. Well, it's not in the schedule. Was it neither of you? Anyway, I decided to go ahead and do a review lecture. I've been really good this semester. I'm right on schedule until I do this review lecture. Now I'm off schedule. But I just want to make sure people are as primed as possible for a good score in the exam tomorrow. So with that said, I know Sandy said that there were some problems with Concept Coach when she was trying to use it, but the Concept Coach would also be delayed because I'm doing a review. So you got another until Wednesday to get that done. And because of that, and the key that the student was actually asking about was not as much about the review lecture as what would be homework due on both Monday and Wednesday was the exact question. And to my brain, that was, are you going to give a review lecture? May not have been the way the student heard it. And so the homework is not due until Wednesday because the homework is not all over stuff on the test. And since I'm doing a review, there won't be homework due from today, so move it on. Everybody clear with those pieces? Okay, so let's look at what we've learned so far this semester. So we are studying electricity. This exam is over chapters 18 through 21, which is about electricity. The next exam will be over magnetism. So chapter 18 is our busiest chapter here. That's where we learned about electric charge. And one thing I've been trying to emphasize this year is that electric charge, I'm trying to emphasize mostly with Sandy, I guess, that electric charge really only means one thing. It means that these particles interact via the electromagnetic force. So if you have a particle that has an electric charge and a gravitational charge, that means it interacts with both gravity and electric forces. And in fact, everything except for photons has a gravitational charge. What do we call that gravitational charge? Mass, right? So something having mass, there are the two technicalities on mass. One is a measurement of inertia. One is that it interacts with gravitational force. And people have found no difference in the two, so we just say mass. So the same ideas that we use with mass being the charge for gravitational force, we start using with the charge for electric force, but there's one huge difference. Electric force can be both attractive and repulsive, whereas the gravitational force was always attractive. So that added a level of complexity. We found that there are two, who really found that there are two types of charge? Ben Franklin. No, not Ben Franklin. He's just the one, I'm sorry, that's wrong. He's the one that identified electrons as a negative charge. Wow. We don't know who found there were two types. It's Ben Franklin that I assigned that electrons have negative charge. Wow. I hate when I make mistakes like that. You notice they're not in my notes here. So rules about these two types of charge. If they're opposite charges, they will attract. So positive attracts negative. We just call the two types positive and negative. That's where we can give Ben Franklin the credit. So positive charge is attracted to negative. Positive charge is repelled by other positive charge. Negative charge is repelled by other negative charge. So when you work problems, you need to pay attention to, since it's a force, both its magnitude and its direction. The direction, you identify by that attracting or repelling. It's never going to have a force that's tangential, right? The force between Katie and me is not going to make me go this direction. It's either going to be attractive or repulsive. And if we have the same kind of charge, repulsive. Opposite kind of charge, attractive. So you do the direction based on those rules, and then the magnitude, use Coulomb's law. So Coulomb's law, just like the force of gravitation, is an inverse square law, not gravity. Force electric is equal to a constant Q1, Q2 over the separation squared. So you should be able to do problems where you're finding the net force on a particle, or you could find the acceleration, right? Because if you have net force, then knowing the mass, you can find the acceleration. Or you could go so far as to say, after it moves this far, how fast will it be going from that information? Then we have the electric fields. The whole point of electric fields is to make life easier. It's learning more, and of course, it's always more difficult to have to learn more. But the electric field's point is to make life easier. Because sometimes when you have a large distribution of charges, calculating the force between this charge and every other thing in the environment is really hard. But if you can find the electric field, which is the result of all of those charges, then you just multiply by the charge by that electric field that results from all the other charges, and it becomes a simple process. So when we learned Gauss's law, we saw there are situations, especially the people in 252 who have done Gauss's law more. There are some situations where it's really easy to find the electric field. And then once you found the electric field, then you can find the force from the electric field. So electric field is defined as the electric force divided by the charge. So if you have a point charge, you can use Coulomb's law for the electric force, right? So if I have a point charge here and I say, what's the electric field over here? I say, well, the force between some charge Q here and charge capital Q there is K capital Q lowercase q divided by the separation squared. Then divided by lowercase q, and I'm left with, for a point charge, E for a point charge is going to be K Q over R squared. And the direction is always going to be pointing out of positive or into negative. And once I found that electric field, I can calculate the force just by utilizing this equation again. We draw electric field lines. Because force is a vector, electric field is a vector, the direction of those lines shows the direction force will be on a positive charge. So you can determine what direction force will be. Remember in class when I used the little applet or whatever, the animation on the computer, that the actual path the particle takes is not the same as the directions of the electric fields, because that's telling us the force, and force is telling us the acceleration, the change in velocity, not the velocity. Because sometimes we just think it should follow the velocity, or the path should follow the electric fields, and it doesn't. But we can calculate the forces by looking at those electric field lines because they tell us the direction, and if they're closer together, it's a stronger electric field, which means you can have more force in the particle. Farther apart, weaker electric field. And then we ended with two things, Gauss's law and conductors. Gauss's law is a statement that says the amount of electric field strength coming out of an object is proportional to the charge enclosed. So we talk about the electric flux, and the flux is a measurement of the area multiplied by the electric field that comes through that area. And so you should be able to calculate the flux and know that that flux for a closed surface is equal to the charge enclosed divided by that permittivity of free space, a constant epsilon sub 0. So that's Gauss's law. The people in the physics 252 may be asked to do more complicated things with it. People in 152 will need to know how it works and be able to calculate something simple like, I have a cube and I have a charge at the dead center of it. How much flux goes through one surface of the cube? Well, since we know that the total flux is going to be the charge divided by epsilon 0, and there's 6 surfaces that are identical, it'd just be 1/6 of the total. You need to be able to solve a problem like that. Or you need to be able to find the flux going, electric fields like this, and I have a circuit like this at this area, or surface like this with a certain area, be able to find that flux, which is given by EA cosine theta, where theta is the angle between the normal to the surface and the electric field. We identify the area as having a direction in the direction of the normal to the surface. So remember, normal to the surface coming out of the surface. Okay, finally, conductors and insulators. We learned, like the first or second class period that a good conductor is something where electrons can fairly freely move throughout the object. And because they can fairly freely move, the electric field inside of a conductor is always zero. Because if it wasn't, there would simply be a force on these electrons that are free to move to make them move until you reach the equilibrium where they're no longer moving. And as a result of that electric field being zero, Gauss's law requires that you have a net charge of zero in any shape you make inside of a conductor. So the charge has to be distributed uniformly so the net charge per unit volume is zero inside of a conductor. So those are rules about conductors that come fairly simply. Insulators, the electrons aren't free to move. And because of that, you can have charge distributed through the insulator in whatever way you manufacture it. And so when we were rubbing things to separate charge, remember charge can't be created or destroyed. When we were rubbing things to separate charge, we were rubbing charge off of the surface of something or onto the surface of something. And that charge didn't move all over the object, it was wherever we rubbed it on or off. And so when I wanted to charge my little electroscope, I had to touch different pieces of my insulator to it to transfer more charge. So know the difference in the insulators and the conductors. And we move on to chapter 19, electric potential and electric field. So electric potential is shifting from a force method of working with electric force to a work energy method of working with electric force. So we're going to now start talking about work energy, and the electric potential is the potential energy per unit charge. So it's in gravitation, that'd be the same as the elevation, because the elevation is the electric potential energy per, well, it's per unit charge in G, right? Have one variation there, but it's basically the same thing. So we talk about this electric potential or voltage because it has units of volts. And she's talking about the potential energy of the charge. Now, the electric potential is positive when you have positive charge, negative where you have negative charge. And since positive charge is attracted to negative, positive charge is going to go toward lower electric potential. Negative charge is going to go toward positive, toward higher electric potential. But in both cases, the charge is going toward lower overall potential energy. So the basic rule of physics, that things go toward lower potential energy, the same as the reason that when I drop this, it goes down, is the reason the charge, if it's a positive charge, it will go toward negative voltage. If it's a negative charge, it will go toward positive charge, because they're going toward lower potential energy. What is better about voltage compared to electric field? Well, number one, just like work and energy versus force, it's a scalar. What does it mean for it to be a scalar?
No direction.
No direction. So the voltage has no direction, which means that when you're working problems, it's easier because you don't have to worry about adding numbers as vectors. You don't have to worry about any directionality. You're just like, well, the voltage is this here, and the voltage is this here. How much work was done? Well, it's potential energy change by difference in voltage multiplied by Q. Right? So it's easier to do the problems. That's why we do it. Something I said earlier today. We try to do things as easy as we can. It's not easy. Right? You guys don't go tell people, oh yeah, physics is easy, right? Probably not. But we try to make it as easy as we can. Then we have the capacitor, or as my friend Nathan liked to call it, the capacitator. There is no such thing as a flux capacitor, just in case that's been bouncing around in anyone's mind since we started this capacitor business. That's a term that was made up for a movie. Just like on that self-same movie, nobody knew how to pronounce giga, and so they pronounce it gigawatts instead of gigawatt, or gigawatts instead of gigawatts, because nobody knew how to pronounce it. True story, they admitted it. So a capacitor is a device that is going to store a charge separation, or, same idea, store energy in the form of an electric field. So it's an energy storage device. And we saw when we did transient circuits how that energy could be delivered. We saw a number of examples. So the energy stored is 1/2 CV squared. And the definition of C is defined as the ratio of the charge separation to the voltage difference across the capacitor. Yes?
You could change the color of the pen.
That not, I was trying to choose the highest contrast I could find. Let me see.
It just hurts my eyes as I'm trying to.
I'm sorry about that. I was actually trying to get the best contrast here. Let's try. Is this better?
Yeah.
Okay. I wanted to be special and use pretty colors today. So we learned for the parallel plate capacitor about the physical capacitance, how the physical dimensions of the capacitor affect the capacitance. That was specifically, the physical capacitance was C is equal to that permittivity free space, kappa, which tells us about the dielectric strength of a dielectric, the area of the plates divided by the separation of the plates. So that kappa brings up dielectrics. Dielectrics, things that have a dipole moment that we use as insulators. When we put something with an electric dipole moment, that means, like my pen, let's say the purple side is negative and the tip here is positive. If Gila is positively charged, I put it like this, which side's going to be attracted to her, positive or negative?
Negative.
Negative. So it's going to rotate like this. And then when it rotates like this, if it's free to move, it'll come toward her because the closer side now is the attractive one. And since it's the inverse square law, if it's closer, it's stronger. And so that's why when we had the Van de Graaff generator here, if you have moisture in the air, it will take charge away from it and it discharges fairly rapidly. Because air, or water, has a dipole moment. Well, in the capacitor, they use dipoles, but they're fixed in place, so they can't move around. So they rotate like that, but now, since this side's negative and this side's positive, it's going to make an electric field from this little dipole that's going from positive to negative. But the electric field that she was making was going the opposite direction. So that dielectric is actually going to decrease the electric field strength in the region where the dielectric exists. The reason you put the dielectric in there as your insulator is because by so doing, you can increase the charge while you keep the same voltage difference. And thus, you have a bigger capacitance. Chapter 20, Electric Current Resistance and Ohm's Law. Now here's something that it won't be on the test, but is useful for you to know. Resistance depends on temperature. The equation for the physical resistance of a resistor, that rho is not the density. It's not the charge density either. That rho is the resistivity, because it starts with R. And so the resistivity is a measurement that tells us how well an object conducts or resists. It has high resistivity, it conducts very poorly, resists very well. And that resistivity changes with temperature. I think it's a plus sign there. So as the temperature changes, the resistance of a resistor also changes. Hence, in a light bulb, the resistance when it's cold, the resistance when it's running are two different numbers. Because the resistivity, the temperature changes a lot. And I would have to check to see if that is a positive or negative sign in there because I didn't look it up. But what I want you to know is, first of all, the resistance does depend on temperature. And the longer your resistor, the larger the resistance. The bigger the area, the lower. And if you think about the water analogy, that's exactly like it is for the resistance of water flowing through a pipe. The bigger the area for the pipe, the easier it is to get water through, the less resistance. The longer the pipe, the harder it is to get it through. So like I said, that's not going to be on the test, but like say you take the MCAT, it could be on the MCAT. So I want to make sure we've got it at least spoken. Now, resistance does not apply to everything. Resistance is only certain materials that will obey Ohm's law. But for things that obey Ohm's law, we had V equals IR. The V is the voltage drop. That is the loss in energy per charge as current goes through. I is the current. And by now, we say current enough. I don't think I need to redefine it. But just in case, current is the rate at which charge is going through. And R is telling us about the actual device that's going through. So obviously, you need to use this a lot. Power is current times voltage. And remember how we defined a resistor? If current is going like this, then we have the plus and minus signs are defined. Because a resistor always dissipates energy. That is, it always removes energy from the charge. So if we look at that, if we have a voltage drop going the same direction as current, then it's dissipating energy. And that energy dissipated is the current multiplied by the voltage drop. If it's a voltage rise as the current goes through, which is what we have in a correctly placed voltaic cell. Remember, the long side is positive. So here the current is going and the voltage goes up as it goes through. You still have the power is voltage times current, but now it's providing, it's putting power in instead of taking it out. So make sure you can calculate power for a circuit. We talked a lot about safety and EKGs. Basic rules of safety. If it's less than a milliamp, you can't even feel it. Is there any danger if you feel electricity? Not necessarily. But if you get up above about 10 milliamps, you start having uncontrolled muscle contractions. I only watched the first half of the Super Bowl yesterday, but there was a commercial for, I think it was add something or other, but it was a TENS device, which is something that you put on, in this case it was on your back, and it then is going to use voltages that it puts there to make the muscles contract involuntarily. You're not telling them to contract, that little device is telling them to contract. And so it's making your muscles pull and push, and that's what happens if you have more than about 10 milliamps. You get up to around 75 milliamps across the heart, and then you run the risk of having a heart attack because your heart runs on electricity. You have muscle, you send an electrical signal to that muscle, and it contracts, depolarizes. And so if you send a signal, the heart's not going to know the difference in, oh, this came from the body, or oh, this came from outside the body. It just says, got that voltage, it's depolarized, and it contracts. And so you can start having involuntary action in your heart, which leads to lack of life. So it becomes very dangerous there if it's going across the chest to 75 milliamps or greater. And remember, we talked about the depolarization first of the atria, and then repolarization of the atria while you're having depolarization of the ventricles. And of course, the depolarization of the ventricles is a huge event pumping blood through the body, and then you have the recovery. I only briefly mentioned the EEG, electroencephalograms. That's putting probes on the melon to measure voltage signals because your brain also runs by electricity. And I don't remember if it was here or somebody else, but somebody was talking. Oh, no, it wasn't. It was Nathan Binkin, who was telling me about research where they were able to put voltages on people's heads and alter their sense of morality and make them think that it was not a problem if you tried to kill somebody but failed. Kind of weird, huh? Because your brain runs on electricity, you can disrupt the way it runs with electricity. All right, moving on, chapter 21. Our last chapter, I'm going to finish early in my review. Circuits. You know, it's a true thing. I've always really liked circuits because circuits are like applied logic, like a puzzle, and I totally dig that. But I have found since I'm a teacher that my students don't, by and large. There are a few that like them, but most of them are like, yeah, they don't see the fun puzzle in it. So when we're working with electric circuits, first of all, make sure that for a battery or a cell, you know what the difference is between the EMF and the actual terminal voltage. EMF, that's that anachronistic term, electromotive force, because they thought that it was putting a force on charge to move it through. And that EMF is the maximum voltage it can supply if there's no current at all. But because your voltaic cell is actually a chemical reaction that's producing the voltage difference, and the chemical reaction does not occur instantaneously, as soon as you start using energy from the battery, its terminal voltage is going to have to drop because the chemical reaction now has to kick into gear to replace the charge that moved away. You know, to give energy, not replace it, you're not creating or destroying charge, but give energy to charge to replace the charge that moved away. And so, as soon as you start flowing current, the terminal voltage drops. The more current you draw, the lower that terminal voltage goes. And so, to model that, this isn't what's really going on, but to model that, we model a voltaic cell as if it has a small internal resistance in series with an ideal battery. So the ideal battery, constant voltage. So that EMF represents the constant voltage of the ideal battery. And then that internal resistance is representing the rate that the reaction occurs. And the bigger that internal resistance, the slower the reaction occurs, and that's the more the voltage is going to drop as you draw current. And of course, as a battery gets old and worn out, the efficiency of that chemical reaction slows down, the internal resistance apparently increases, and that's when you know your battery is starting to fail. So make sure you understand those things about the battery. Then we have Kirchhoff's laws. What is Kirchhoff's voltage law? Sum of the voltages in a loop is equal to 0. And that's a restatement of which law that we already learned? Conservation of energy. What about Kirchhoff's current law? Sum of the currents in a node equals 0. And that's a statement of conservation of charge. So those two laws, combined with Ohm's law, allows you to solve any complicated circuits. And so you will almost certainly have a complicated circuit that you have to solve on the test. So make sure that you can go through those steps. Gabriel.
Why are those interchangeable? Why is his voltage law not also an example of conservation of charge, or vice versa?
Okay, so let's go with vice versa first, because that's the easy one for me to answer, because I know the answer to that everything. Kirchhoff's current law is simply counting, if you will, counting balls. If I have 5 balls in, I have to have 5 balls out. If I have 10 balls in, I have to have 10 balls out. It doesn't matter what their energies are. Right? So it doesn't deal with energy at all. It only deals with the number that comes in has to be the number that goes out, because I can't create or destroy the charge. And my node is certainly not going to be storing it up. Now, with the energy, the voltage, you can have energy changes in a circuit, right? And you can have energy changes here differently than there. And for the voltage, we're looking at, okay, so if we start and end, we have to be at the same energy. It doesn't matter how many balls do it, it's just that we have to get back to the same energy. So that's the harder one for me to answer. Obviously, the first one I think was a much clearer answer than the second one. But yeah, they're different ideas. Now, I skipped the first line here. Make sure you can actually show how we derive resistors adding in series and resistors adding in parallel? I'm not saying that's going to be on the test. I don't know if it will or not. But that's a skill that you need to be able to do, combining resistors and understanding why they combined the way they did, not just, well, it was a magic equation. Right? Because if you learned it's a magic equation, then you didn't learn physics, you learned math. Okay. Will you have to use linear algebra on your calculator? It will be the difference in probably 1 point if you can't do it versus if you can. So don't make that the point of 2 hours of study. Make sure you can do it on your calculator. If you can do it, great. If you can't do it, well, there are other ways to solve the problems. They're just more time consuming. And if you have all the right equations, that's going to be, assuming that you got them and have explanations of how you got there, that'll be 9 out of the 10 points already. So don't freak out like, I got the equations, I don't know what to do with them. If you can find the appropriate equations and explain why these are the appropriate equations, that's the vast, vast majority of the points for the problem. Voltmeters and ammeters. Ideally, well, let's start with the beginning. Voltage measurements are the difference between the two sides of an element. So because you're measuring the difference between two sides, how do you connect a voltmeter, series or parallel? Parallel. But when I connect it in parallel, now I have an alternate path for charge to go through. And so I could then have some current that instead of going through my original resistor goes through my voltmeter. So ideally, what should the resistance be of the voltmeter to stop that from happening? Infinite. So a voltmeter ideally has an infinite resistance. In practice, depending on your voltmeter, it might be in the giga-ohm range, it might be larger. And there are some really precise voltmeters that actually have an effective resistance that is infinite. They actually provide a reverse voltage and measure the voltage necessary to make the current in it zero. If you make the current in it zero, then by definition, that's effectively an infinite resistance. So those are more expensive meters, but they're better meters for sure. Now, an ammeter, you're measuring the current that's going through a resistor. So I have this resistor, and I want to know how much current is going through, how I have to connect my ammeter in series, which means the current is going through it. But then, if I have a resistance with current going through it, it's going to remove some energy. I can have voltage drop. So ideally, what would the resistance be of an ammeter? Zero. So because the resistance of an ammeter is ideally zero, what happens if you put your ammeter in parallel with your device? All the current bypasses this device and goes through the ammeter with no resistance. So if you were to connect it to the power supply, you would draw all of the current the power supply can supply, and you would burn whatever you connected to it. That's bad. And that's why you need to be careful with measuring currents. Measuring voltage is fine. You can take voltage probe, stick them in here, be careful that you don't shock yourself, and you'll be fine. If you hold the wires, then you won't be. But if you're insulated, it'll be fine. You do that with the ammeter, and you have big troubles. The last thing, transient circuits. Transient circuits was a resistor and a capacitor. Soon we'll learn about a resistor and an inductor is another transient circuit. Inductors are devices that store energy in the form of a magnetic field. And so they're the same idea, storing energy, just in a different type of field. So the transient circuits, we went through what the voltage drop looks like. You start with a capacitor, can't have an instantaneous change in its voltage. So if you start with 0 voltage on the capacitor and you flip a switch, the instant you flip the switch, it's still going to be 0 voltage on the capacitor, and you can calculate the currents going everywhere. And once you've done that, then you know that the current flowing in the capacitor charges up the capacitor, which means that you're going to decrease the currents, and so the rate of charging slows over time. And that gave us the equations, which will be on the test, that say the voltage is equal to where V0 is the voltage across the capacitor when you first flip the switch, and V infinity is going to be the voltage across the capacitor after it's been there for a very, very long time. How much current will flow through the capacitor after it's been a very, very long time? 0. Technically, no current ever flows through a capacitor, but you have current flowing to it when it's charging, current flowing away from it when it's discharging. And so we talk about the current of the capacitor, even though technically nothing's flowing through it. It's flowing to it or flowing away from it. And the fact is, if it's charging, it's flowing to one side and leaving the other side. So it looks like you have current going through it, even though it's not. Tau is called the time constant. It's called the RC time constant because it's the resistance times the capacitance, RC. And so if you have a bigger RC, it's going to charge and discharge more slowly. Smaller RC, charge and discharge faster. So I used in class the example of a disposable flash system. You have a battery, a capacitor, and it charges very slowly. So it has a large resistor for charging. It discharges very quickly so that you get a large deposit of energy, has a small resistance for discharging. That's it for my review, except for let's just review how you take the test, how you answer the problems. So everybody by now knows, well, let's make sure you understand the theory. What am I looking for when I'm grading your test problems? Yeah, I'm looking to see that you have shown that you understand how it works, not that you can do the problem. A lot of times people can do a problem, they don't know how it works, but they just know, well, I did that before, I'm going to do it again, don't know why. So I'm looking for you to illustrate that you understand how it works, the whys of it. That's the physics. And so that's why we have, the first thing is draw a picture, show the physical system. And that picture needs to be something that's illustrating what you need to solve it. So sometimes you can have a picture that's accurate but doesn't relate to the solution. So, think about your figures and make sure, this is a picture that's going to help to show what's going on and help you solve it. And then you have the concept part. The picture is generally 2 points. If it's not required, I will actually have a statement saying you don't need a picture, so you always know. If it doesn't say that, in my mind, there was a picture that is going to help you solve this, and you think about what that picture would be. Then we have the concept. The concept is what ideas are going into this. It doesn't need to be half a page. I mean, it can be. No, I'm kidding. I'm kidding and giving Jordan grief. I'm not kidding about, it doesn't have to be half a page, but it needs to show that you understand what the ideas are and how they're going to fit together for solving this problem. And then you have the equations, which really should be an extension of your concept, because your concept said, well, I'm going to calculate the energy stored, and then you say, well, so the equation for the energy stored is this, right? So the equation should follow from your concept. And then you have the math, putting the numbers in, and getting your answer. And so the points typically, 2 for the figure, 3 for your concept, 2 for choosing the right equations, 2 for doing the right math, 1 for actually getting the right answer. What happens if there's no math involved? It adds to which one? Concept, yeah. If there's no math involved, it goes to the concept. If there's no figure involved, it goes to the concept. The concept, since that is really my goal to see that you understand it, anything that's missing, the points go to the concept. Okay, so I want to make sure, once again, that it's clear how I'm grading. At this point, I don't think anyone's going to be confused except for maybe Jared. Okay. But I want to make sure there's no confusion. Don't be like, I didn't know that I needed to do that, because that always hurts me. And of course, it hurts the students as well. Okay, any questions, things that you want to know?
You say small RC, I forgot what that was called, value that, thank you, Tau, allows it to charge and discharge faster.
Right,
okay.
right. If you have a small R times C, then you'll have faster changes.
Okay.
Jordan.
In the book, that equation is just written V equals V.
Yes, the reason I put it this way is because this covers every possible scenario, including with an inductor.
Okay.
With an inductor, What's the only thing that's going to be different is, oh boy, there it is for an inductor, it's tau is equal to, I think it's L over R. But the equation still works exactly the same.
So if we were to leave out the V infinities, would you take points off of that?
No. I'm just putting the most complete. And while I'm at it, the current follows the same equation. And once again, that will work in any situation. Current infinity is always 0 for a capacitor. But those are the way the equations are going to show because they work in every possible situation. Okay, I'll see you here at 2 p.m. tomorrow for the exam.
Oh, and how would still be RC?